Hello everyone, my name is Zheng and I'm a PhD student at Northwestern University. Today I will present our papers, CAMP, Compiler and Allocator-based Heap Memory Protection. And the first author of the paper is Zhenpeng. In the domain of software development, a notable majority of programs are developed by the unsafe language such as C and C++, which will grant detailed control of low-level operations and memory management, also invariably expose them to a range of vulnerabilities. Google Project Zero discovered that heap-based heap errors accounted for 69% and of zero-day vulnerabilities observed in the wild, and 65% of vulnerabilities are confirmed as heap-based errors. So we proposed CAMP. CAMP is a defense mechanism designed to render out-of-bound and user-free vulnerabilities unexploitable, also while provide the low performance overhead. Then, first we introduce how CAMP provides the temporal security. CAMP prevents user-free by notified dangling pointers. At runtime, CAMP constructs the point-to relations by instrumenting the program. When a memory project is freed, CAMP could look up the build-to relations and identify the dangling pointers to the freed memories. By notifying those dangling pointers, user-free access is no longer possible. Copying pointers is tracked to build point-to relationship. For example, in this code snippet, when the allocate function trying to allocate a pointer, then it stores the pointer to the variable bus. CAMP will instrument the tracking instruction to store the point-to relations. And when the program frees the memory, inside the freeze, CAMP will identify the exciting dangling pointers to the freed memory and notify them as non-accessible. As a result, the variable of bus is no longer referenced to the freed memory, and the program crashes when the pointer is dereferenced. To further boost the overall performance of CAMP, we designed a cache mechanism for maintaining the point-to relations. New point-to relations are temporarily stored in a cache until it becomes full, at which point the records are transferred to the allocator in a batch while skipping any duplicates. This cache boost the runtime speed. This cache can boost the runtime speed because the program usually generates many similar pointer relationships frequently, so the cache can efficiently skip these duplications. Then we introduce how CAMP provides the spatial security. The base of the spatial security is provided by the scalist allocator. A scalist allocator uses different free lists for different sizes of memory projects. The allocator, for example, the tcmalloc, uses spans as the unit memory management. Each span manages a size of class memory objects on server continuous memory patches. So we save the base address and the size of each span. By utilizing this metadata, we can calculate the boundary of each pointers. So when giving a pointers, we can calculate its boundaries in the runtime. To further optimize the boundary checking optimization, we utilize many compiler optimization techniques. The first we introduce how we insert the checking. We insert checking at the point arithmetic side instead of the point dereference side. The example shows how we instrument the checking. There are two types of point arithmetic instructions. The first is the typecasting. In this example, the program trying to malloc a void pointer. Then, since the target type is the struct object, so the LVM will insert a typecasting instructions to typecasting the void pointer to the typed pointer. So we insert an instruction to check if the pointer can at least contain one object. Okay. And another type of point arithmetic instruction is the common point calculation as the example. Then we introduce how we use optimization technique to optimize the camp. The first optimization is the type optimization. As we said before, we instrument checking for every typecasting instruction. So we know that for every live typed pointer, the memory space referenced by the typed pointer is always adequate for its corresponding type. Because we always insert the checking instructions at the typecasting site. So after that, we can simply remove the two checking because the two point arithmetic instruction is used for index the internal field of the structure. The second optimization is the merge optimization. We know that since that we always need to fetch the boundary of each point first, then check if the result pointer overflowed or underflowed. So if our compiler notes that multiple pointers are generated from the same base pointer, in this example, the line 5 and the line 7, the PTRI and the PTRJ, both of them are generated from the PTR passed from the external of the function. So we can fetch the boundary of PTR first. Then we can only insert the simplified checking for the following two point arithmetic instructions. We do not need to the boundary information from runtime again. By the way, we also have two extra optimizations. Due to the time limit, we do not expand them here. You can reference them in the paper. Okay, then we did a security evaluation on the real-world vulnerabilities. CAMP successfully detected and prevented all user-free vulnerabilities. In the case of heap overflow vulnerabilities, CAMP also prevented all of them. We also did the performance evaluation on SPEC CPU 2070. We utilized the geo-mean value to represent the average overhead of each system, and CAMP also gets the best performance overhead of 21%, while other tools like ASAM and ESAM and memcheck provide higher overheads. Okay. Besides, we also did ablation study. The ablation study shows the overhead or when disable each optimizations. We can note that when disable each optimizations, the overhead is largely increased, which shows the optimized performance of each optimization and in our system. Okay, in summary, our paper pros CAMP, which employs a customized allocator and a compiler to safeguard against the heap memory corruption, and we implemented it based on the tcmalloc and LVM12. And about the evaluation, we tested on the engines and spec benchmarks assessed for security and runtime overhead. I also compared it with previous defense solutions. Okay, that's all. Thanks for your attention. There are some information about me. Welcome any questions. I will.